back students once again to Ask IITians. In the previous lecture, we have studied all about the different kind of processes, different kind of systems and the other terms which were associated with thermodynamics. Now, in today's lecture, I have thought of discussing what are the different laws of thermodynamics. There were basically 4 laws which were given for thermodynamics, and I'll be taking into account all these laws one by one. Then at the end of the chapter, we'll also be doing certain questions about thermodynamics and those laws. So let me try beginning with the session so that you can get to know what are the different laws. Once you know these different laws, you will be able to solve as many questions as they are asked in the exams. So let's start with the session. Now, having discussed about all the thermodynamic terms, like what are the system, what are the surroundings, what are the properties, what are the different processes, now it's a time when we should come over to what are the different laws of thermodynamics. So actually 4 laws of thermodynamics have been proposed. Let us start with the very first law, which is basically given as the 0th law of thermodynamics. Now let's start. What do we mean by the 0th law of thermodynamics? It says that when suppose you have a body A and this body A is in thermal equilibrium with another body, say body B. Now this body B is found to be separately in thermal equilibrium with say a body C. Now if A and B are in thermal equilibrium with each other, that means A and B are at same temperature. And if B and C are further in a thermal equilibrium with each other, that means that this is possible if and only if body A and C will be in thermal equilibrium with each other. So this, whatever I have explained in the above paragraph, this is known as the 0th law of thermodynamics, and this is the basic principle of temperature measurement. For example, when we use a mercury thermometer, which was used in the earlier days, so the basic working principle of that mercury thermometer is the same of 0th law of thermodynamics, where the mercury in the glass is brought in contact with your body. So the body temperature, the body gets in thermal equilibrium with mercury, and hence it increases in the level, and hence you will be able to measure the temperature in the thermometer. Now once we have discussed the 0th law of thermodynamics, is the time when we should come over to the first law of thermodynamics. The first law of thermodynamics is the application of conservation of energy principle to heat and thermodynamic process. So like whatever we say, right, the energy can neither be created and it cannot be destroyed. That means there is conservation of energy in the system and the surrounding. So this is what is basically dealt in the first law of thermodynamics. So it says that the change in the internal energy of the system is equal to the heat added to the system minus the work done by the system. So this was the definition. Now let me explain how we calculate the internal energy of the system. Suppose you have any particular system. Let us say you have a container and you have enclosed some gas inside the container and you have covered it with a piston. Now you know that all the gaseous molecules, they are continuously moving. So they possess some kinetic energy, they also possess some potential energy. That means even without you heating the system to any particular level, the system already has some amount of energy with itself. That amount of energy which the system possesses because of the virtue is known as internal energy, which is basically given by the symbol E or U. Now we say that if you are doing some work on the system or if the work is done by the system, if you are providing some heat to the system or if the heat is provided by the system, whatever change you will be making in the terms of energy and work, in the terms of heat and work, these total changes are going to be accountable for the internal energy. So I will write U is equal to E, which will be written as Q plus W, where we'll say the change in internal energy, I'll say delta U. Since we are talking about the change, I can simply say du will be equal to dq plus dw, or delta U is equal to delta E, which will be equal to Q plus W. Where if heat is added to the system, you will be putting a positive sign, and if the work is done by the system, you will be putting a negative sign. And hence we come over to the first law of thermodynamics, which basically deals with the conservation of energy. Let's try to have further discussion. See, here we have written it again the same thing. Delta U, which is change in internal energy, is equal to Q minus W. This is what I tried to explain. Now once we are done with this thing, let us come over to what are the limitations of the first law. This was the first law we have discussed. Let's now try to discuss what are the limitations of first law. See, the first law doesn't tell us whether any particular process is actually going to occur or not. For example, I say that there is a reaction A plus B is going to form C. But if using the first law, I can just predict, okay, whatever are the energy change taking place inside the system, how the internal energy of the system is going to be changed. But the first law doesn't give me any information whether actually the process is going to occur or not. According to the first law of thermodynamics, so the heat may flow from higher temperature to lower temperature and vice versa. That's quite obvious because the first law considered only the flow of heat. That means you can always talk of the flow of heat either from a body of high temperature to a body of low temperature. Also, according to the first law, you can talk of the heat movement from a body of low temperature to a body of high temperature. Practically, we know that heat cannot flow from a body of low temperature to a body of higher one. But this cannot be so called as a predicament of first law. Like practically, you know, right? If the temperature of the surrounding is say 10 degrees Celsius and if you are keeping a beaker which is containing water at 100 degrees Celsius. So for sure the heat will be transferred from the beaker of water to the surrounding. Rather than you saying that no, surrounding will come down to 5 degrees and the temperature of the beaker is going to increase to 105. That's not possible. So this was the limitation of first law. Now, if I discuss further more limitations, I will say that according to the first law, we can convert 100% of the heat which is available to us into work and again vice versa. For example, if there is a system with a piston arrangement, there is some gas inside the piston, inside the container. And if I am saying you are heating the container, that means you are providing heat to the gaseous substance. So according to the first law, whatever is the amount of heat you are providing to the gas, every part of that heat will be converted into work. Like it will help in moving the piston in the upward direction. But practically we know that again this is not possible to do. So the first law of thermodynamics does not restrict our ability to convert heat into work. According to first law, if you have work, you can 100% convert it into heat. If you have heat, you can 100% convert it into work. But practically this is not possible. That means the first law has got some limitations. That is why we need something else. So the above quoted handicaps, these lead to the formulation of another law of thermodynamics and hence we'll be studying something known as second law of thermodynamics. So coming over to what do we actually mean by second law of thermodynamics? See, it's impossible to construct any particular device which, like if there is an operation in the cycle, has the sole effect of extracting heat from a single reservoir and performing an equivalent amount of work. So there was a statement given by Kelvin and Planck which is known as Kelvin-Planck statement, and this says the same thing. Like we know, if you have heat, you can never ever convert it into 100% of work. And the same thing vice versa is also not possible. Like there is 100% conversion of heat to work is not possible, and also 100% conversion of work to heat is again not possible. So you can say, in other terms, the second law of thermodynamics says that it is impossible for heat to flow from a cooler body to another hotter body without any aid of external agency. And this is what is Clausius' statement. Let me repeat the statement again. For example, you have a beaker and you have water in the beaker at say suppose 90 degrees Celsius and the surrounding temperature suppose is 25 degrees Celsius. So this says that if you have a body at higher temperature, this is what we know practically, that heat will flow from a higher temperature body to a lower temperature body. That's obvious. But the second law of thermodynamics says that if you want the flow of heat from a lower temperature body to a higher temperature body, like if you want this beaker of water to be raised to at least, for example, 100 degrees Celsius, you need to provide any external agency which can do this work. So without the aid, without the help of any external agency, to flow the heat from lower temperature body to higher temperature body is not feasible. This is what is said by second law. Now let us come over to the last law of thermodynamics. Let's see what the last law of thermodynamics says. This is known as the third law of thermodynamics, according to which the heat capacities of all the solids tends to zero at absolute zero of the temperature is approached, and the internal energies and entropies of all the substances become equal there, approaching their common value asymptotically. Now what is being said here is, suppose I say that there is a container which contains some gaseous molecules. I told you in the beginning of the first law that even if you do not heat the container, all the gaseous molecules will have certain kind of energy. Now suppose instead of taking the gaseous molecule, I have taken any solid material. Now if I have taken any solid material, that means all the molecules are properly packed. So if you are trying to cool the system and you take the system to a very low value, let us say 0 Kelvin, which is also known as absolute 0 Kelvin, because below this temperature nothing is attainable. You cannot go below 0 Kelvin. Even approaching 0 Kelvin is very difficult. So I say that if you are taking your system to 0 Kelvin, all the molecules are going to settle down very nicely. That means they are not going to show any movement into their atoms or molecules. They won't be vibrating at all. So at absolute temperature, at absolute 0 Kelvin, the entropy possessed, entropy means the randomness, the way with which a particular molecule is vibrating is a measure of entropy of the system. So if you are approaching to 0 Kelvin, the entropy of the system is going to be 0. That means everything will settle out quite nicely. This simple statement follows neither the first law, that law of conservation of energy is not followed here, and nor it comes from the second law. So what we say is that this is a new kind of law, and hence this has been named specifically as third law of thermodynamics. So let us continue the discussion over the third law of thermodynamics once again. This theorem is quite useful in explaining the nature of bodies in the neighborhood of absolute 0 temperature. This is what I just explained in the previous slide. That just suppose even at 1 Kelvin temperature, the molecules still possess some amount of energy that they will be vibrating from their mean position. And hence they will be having some amount of entropy associated with them. But as soon as you move from 1 Kelvin to even lower, 0 Kelvin, all the entropy, all the energy possessed will come to a halt, it will come to 0. So its importance basically lies in the fact that it permits the calculation of absolute values of entropy and the physical interpretations of thermodynamic properties such as Helmholtz free energy and Gibbs free energy. So these are different kind of energies. Like we have studied something, what do we mean by internal energy, the total energy possessed. There are some other forms of energy like enthalpy, the Gibbs free energy, which are very much useful in the thermodynamic details, in the thermodynamic studies. So to predict their physical significance also, this third law of thermodynamics is quite efficient and quite important. Once again, coming over to this thing, it can be convinced that as the temperature of the system tends to absolute 0. For example, you just started from 300 Kelvin and you're moving down, let's say to 200 Kelvin, you moved further down to say 100 Kelvin and finally you came down to 0 Kelvin. That means as the system is approaching 0 Kelvin, its entropy tends to a constant value which is independent of pressure and the state of aggregation. So whatever will be the entropy value possessed here, whatever is total entropy, it's gonna decrease, and as soon as you move over to 0 Kelvin, the entropy is gonna possess a constant value. It won't be changing. So we may put it equal to 0 so that entropy of every substance become normalized in an absolute way. It might be having some value, but to deal in theoretical as well as in practical terms, you consider it to be 0 so that at absolute way, everything is said to have a 0 value of entropy at 0 Kelvin. Now let us consider the illustrations which we are going to do for whatever we have studied till now. So the first illustration that we are going to discuss is, consider that 214 joules of work is done on the system. Now this is a pretty good question because here I'll be telling you something about the sign conventions which are generally used in thermodynamics. See, since we are working with work done and we are working with heat, now I will say, if the work is done on the system, it will be given a positive value. If the work is done by the system, it will be given a negative value. Similarly, if heat is inserted to the system, it will be given a positive value. Whereas if the heat is given by the system, it will be given a negative value. Now let us take the question into consideration. He says that 214 joules of work is done on the system. That means W will be plus 214 joules. And if 293 joules of heat is extracted from the system, so Q is given to be minus 293 joules. In the sense of the first law of thermodynamics, he asks us to calculate what are the values including the algebraic signs of Q, W and En. So this is the value of Q, A part, we are done. This is the value of W, B part, we are done. Now let us come over to the C part where he asks us to calculate the internal energy value. Now we know that U is equal to Q plus W. So since this is minus 293 joules and W is 214 joules, so on solving this you will be getting minus 79 joules. That means the internal energy has got a value of minus 79 joules. So this was all about the first illustration. Let us come over to illustration number 2 where he says 1 mole of an ideal monoatomic gas at 27 degrees Celsius, that means 300 Kelvin is given to us, is expanding adiabatically against a constant external pressure. Now the external pressure is given to be 1.5 atm from a volume V1 of 4 decimeter cube to V2 of 16 decimeter cube. Now he asks us to calculate the values of Q, W and delta U. Now that's quite simple again. We know that since the work is done adiabatically, the system is adiabatic, so no heat exchange is taking place. So I'll say Q is equal to 0. Now, since the work is done against a constant external pressure, so we have always discussed in physics, like in our previous chapters, that the work done is minus P external dV. So if the work is done against a constant external pressure, so W will be minus P external, that means minus 1.5 atm. dV means V2 minus V1, so I'll write minus 1.5 atm. Final volume is 16 minus 4 decimeter cube. So the answer will come out to be minus 18 atmosphere decimeter cube. Now once again the third part says that you need to find out the value of delta U. So we can say delta U is Q plus W, 0 minus 18 atm decimeter cube. So the overall answer comes out to be minus 18 atm decimeter cube. So this was all about how we are going to use the 0th, 1st, 2nd and the 3rd law of thermodynamics in the illustrations. Now we'll proceed ahead with another topic as heat engines. Students, you have seen that we had a discussion of what were the different laws of thermodynamics. thermodynamics. We have taken into account the 0th law of thermodynamics, the first, second and the third law of thermodynamics. We also try to deal with what do we mean by entropy, internal energy, Gibbs free energy and other terms. Now, we had also done certain questions which are generally asked in the exams. So, in all the competitive exams, you will be asked the applications of these 3 and 4th law of thermodynamics. Now, in the next session, I will simply try to discuss about the practical applications of thermodynamics, where I will tell you something about what do we mean by heat engine, Carnot cycle, how a refrigerator works and what are the different kind of processes in thermodynamics which are used for applicative parts. Now, I'll simply suggest you so as to revise whatever has been taught to you till now so that we can use up the entire knowledge and come over to the last section of this chapter. So by the time, stay tuned and I hope to see you in my further lectures.